Question 8. So we've got a proton turning into neutron and the weak exchange, which is W plus boson. You're going to get a beta plus and electron neutrino, and so here will be the beta plus, which you have there already. Y will be the electron neutrino and X will be W plus. So the answer is A. Note the charge on the lepton on beta plus is -1 and the lepton on the electron neutrino is +1. So that's conserved. Charge is conserved, and so this is A. Question number 9. The electron collides with an isolated atom and rises an orbiting electron to a higher energy level. Which of these statements is correct? The colliding electron is captured by the nucleus of the atom. That's not going to be correct. A photon is emitted when the electron rises to the high energy level. That's not correct. We've got an electron is emitted when the excited electron returns to the ground state, and that's not correct also. And the energy is transferred from the colliding electron to the orbiting electron. That's correct, so that's going to be D. Question 10. A light of frequency 2 × 10⁻15 Hz is incident on a metal surface. The work function of the metal is 4.6 × 10⁻19 joules. Which statement is correct? So the first one is we've got no photon electrons are released. Well, so we need to be able to work out if it's a work function, you expect photon electrons to be released. And B, photon electrons are released with a maximum kinetic energy of, so we need to work out the maximum kinetic energy that the photon electron were released with. So we know that the formula we use is E equals work function times the maximum kinetic energy. And the work function, the E is HF, which is equal to work function plus maximum kinetic energy. So therefore we can rearrange, make kinetic energy the subject. So we get HF equals HF minus work function. We know what H is, 6.63 × 10⁻34 times F, we're given 2 × 10⁻15. And then you take that away, the work function, and we get 8.66 × 10⁻19 joules, which is going to be C. Number 11. For number 11, we've got a photon of ultraviolet radiation has a frequency of 1.5 × 10⁻15 Hz. What is the momentum of the photon? Well, momentum, we're looking for momentum, we know the lambda, so we know that lambda equals h over momentum. So lambda is h over momentum, which means that momentum will be h over lambda. We know that lambda or c equals f lambda. We can make lambda the subject here. That will be c. Lambda equals c over f. Replace lambda with c over f here, and then we get hf over c. So therefore momentum is hf over c. Plug in the Planck constant in there times the frequency times the speed of light, and we get the momentum to be 3.3 × 10⁻27 kilograms meters per second, which is C. So number 11 is C. Question 12. Which statement about a couple is not true? A, it must consist of coplanar forces. B, it can produce rotational motion. So A and B is correct. C, it can produce translational motion. So coupling is not going to produce translational motion. D, it has a moment with unit Newton's meter. So A, B, and D are correct, but C is wrong. So the answer is C. Q leaves at time t equal to 0 and P leaves 1 second later. The figure shows the velocity time graph for P and Q. What is the distance between Q and P when t equals 8 seconds? Well, for a velocity time graph, to find the displacement or distance, you find the area under the curve. So what we need to do is to find the area under the curve, and we can find the area under Q. So we could say this is Q here at 8 seconds. So we want to find that area Q, and that is what we've got here, dq, that's distance or displacement, equals 40, because the height here is 40, so that's 40. That's velocity. So that's 40 times 8 divided by 2, because it's a right angle triangle. So, and that gives 160 meters. And that's for this distance for Q. And for P, we need to add the two distances we're going to calculate from 0. For P, we're going to calculate for 1 to 3. 1 to 3, so that's 3. So that difference is 2. That's what I meant. And from then we have 5 for 3 to 8. So that distance is 5. And that distance is 2. And the height here for that one is 20. So we want to add the two areas together. And that's what we got here. So we've got a half, because that's a right angle triangle. So a half, 20, the height, times 2 divided by 2 plus the rectangle, which is 20 times 5, and that gives 20 plus 100, that's 120. So the difference between the two of them is going to be 160 minus 120, which is 40 meters. So the answer is A. Question 14. A 0.2 kilogram mass is suspended from a spring. A 0.1 kilogram mass is suspended from the 0.2 kilogram mass using a thread of negligible mass. The system is in equilibrium and the thread is then cut. So when the thread is cut, what is the upward acceleration of the 0.2 kilogram mass at the instant that the thread is cut? Well, initially, the force on the tube will be 0.3 times the gravitational field strength. And when it is cut, then the force is now going to be 0.2 gravitational field strength. And so the difference between the leading force now will be 0.1 gravitational field strength. So what we now need is the 0.1 gravitational field strength. So that means F equals ma, and A is going to be F over m, which is 0.1 gravitational field strength, the F, over the mass 0.2, which is what is got left. And therefore, multiply both sides by 10, you're going to get G over 2, which is 4.9 meters per second squared. So the answer is B. Question 15. A lift of mass m is suspended by a cable. The lift descended with a downward acceleration A. A frictional force F acts on the lift. What is the tension in the cable? Because the mass, the weight of the lift, mg, is the leading, in this case, the weight is leading. Because it's leading, we have to, and this is indicated by the acceleration. Therefore, we have to start with the leading, which is mg, minus the tension, because tension is pulling it back, and minus friction, which is also pulling it back, equals ma. Therefore, mg minus F minus ma equals T. So because we want to make T the subject. Now, common factor is m. So that would be G minus A, open bracket, M, close bracket, minus F. And that's what T is. And the answer is D. 16, question 16. A body of mass M falls freely due to gravitational field strength. The rate of change of momentum of the body is equal to its, well, so the force is equal to mass changing momentum over time. And therefore, you might say force is equal to the rate of change in momentum. And we're looking for force. And kinetic energy is not force, mass is not force, gravitational potential energy is not force. Weight is force, so the answer is going to be D. 17. An electric vehicle is driven by a motor which produces a constant driving force. The vehicle travels from rest along a straight horizontal road. Friction and air resistance are negligible. Which statement describes the variation with the time of the power developed by the motor? A, it stays constant. No. B, it increases linearly from 0. C, it increases non-linearly from 0. And D, it increases from 0 to a maximum and then decreases. Since we're looking for the fact that the vehicle was produced at a constant driving force, it will increase linearly from 0. So the answer is going to be B. Question 18. Well, which is a correct statement about mechanical power? Well, mechanical power is energy over time, and energy is work done. So that's force times distance over time. But the distance over time is what we call velocity. Well, displacement over time is velocity. Distance over time is speed. So force is ma times the velocity or speed, m times av, where the unit for that is going to be kilogram meters per second squared, meter per second, and all together gives kilogram meters squared per second cube. So the answer is C. 19. A load of 50 newtons is suspended from a wire that has an area of cross-sectional of 1 millimeter squared. The stress in the wire in Pascal is between. Right, so we need to find the stress in the wire. Stress is force over area, where the area is 1 millimeter squared, which means it's 1 millimeter open bracket square, which is 1 times 10 to the power minus 3 meters all squared, and that is 1 times 10 to the power minus 6 meters. Force is 50 newtons. Stress is 50 over 1 times 10 to the power minus 6, which is 50 times 10 to the power 6 newtons per meter squared. Stress is now 5 times 10 to the power 7 newtons per meter squared, and it's between 10 to the power 6 and 10 to the power 9. So the answer is C. Question 20. Which combination of properties would produce the smallest extension of a wire when the same tensile force is applied to the wire? Well, so we got the E is stress over strain, and that's the equation. So we know stress is force over area over extension, changing extension over length, and we obviously rearrange that. We get E to be F times L over A times extension. Now we're making extension the subject. We got F L over EA. But F is constant for all four conditions. So the first condition is A, where we got 3, length is 3L, so that's 3, and E is 1, and extension is 1, that's just 3 times. B, we've got the length L, which is 1, and we got 2 for the cross-sectional area, 2 times 1 for the energy, and Young's modulus, so that is basically a half. For C, we got 3 for length, and we got 1 for the cross-sectional area, and we got 4 for Young's modulus, and that's 3 over 4. And we look at D, which is L is 1, and cross-sectional area is 2, and E is 4, and that's 1 over 8. So the D is the smallest, which is 1 over 8. 21. A rubber belt in an electrostatic machine has a width of 0.1 meters and moves with speed of 0.4 meters per second. Each square meter of the belt carries a charge coulomb, and the charge is removed and transferred to a metal sphere. What is the charge collected by the sphere each second? So we're looking for, we got the distance here, 0.1 meter, and we got the velocity, 0.4 meters per second. If I multiply the velocity times the distance, I'll get 0.04 meters squared per second. The reason why I've done that, because I'm looking for 1 meter squared. So a meter squared, I can get that by multiplying these two together per second. So that's 0.04 meters squared per second. All I now need to do is move from 1 meter squared to 0.04 meter squared. So multiply that by 0.04, I get 0.04 meters squared, and 1 coulomb will be times 0.04 will give me 0.04 coulomb. So therefore the answer is going to be B. 22. Charge plate X and Y have a potential difference of 1.5 volts between them. Which particle gains 3 electron volts of kinetic energy when moving from Y to X? Is it going to be a proton? Proton is got plus 1 charge, so it wouldn't double the potential, electric potential energy. So electric kinetic energy. So positron is positive, so again that will not double because it's just got plus 1. Electron is minus 1. Alpha particle is plus 2. Because alpha particle is plus 2, that charge is doubled, and therefore this will double the kinetic energy. So it's going to be D. Question 23. The diagram shows part of a circuit and the currents in this circuit. What is the potential difference between P and Earth? So this is Earth. We have to work out potential difference. The current going in here at this junction here, Kirchhoff's law, and the current coming here, so that's 4 amps plus 2 amps coming up there, and that will be 6 amps, and that 6 amps is going through the 20 ohms, where we can apply V equals IR. That's 6 times 20, that's 120 volts. So the potential here is 120 volts. But coming from there is 2 amps through to 10 ohms. So V equals IR, that's 2 times 10, that's 20 volts. So that's 20 volts, and that's 120 volts. And the total voltage between the two is 140 volts. So the answer is going to be D. Question 24. A voltmeter has a resistance of 4 kilo ohms and reads 1 volt for every scale division on the meter. A power supply of EMF 20 volts and negligible internal resistance is connected across its voltmeter and a resistor in series. The voltmeter reads 2 division, which means it's going to be 2 volts for every 1 division is 1 volt. What is the value of the resistor? So V equals IR. They have the same current flowing through them, so current is constant. For V1 over R1 is going to be equal to I. V2 over R2 is also equal to I. Therefore, V1 over R1 is equal to V2 over R2. R2, which is what we're looking for, is going to be V2 over V1 times R1, which is 4 times, that's 4 kilo ohms, just leave that as kilo ohms, times, because we've got a ratio of the voltage here, times 18 over 2, and that would be 36 kilo ohms. So the answer is B. That would be 36 kilo ohms. The answer is B. 25. 2 cylindrical wire P and Q are of equal length and made of the same material. The diameter of P is greater than that of Q. P and Q are connected in series, and the ends of this arrangement are connected to a power supply. Which two quantities are the same for P and Q? Well, we know they have the same material, so their resistivity will be the same, and it will be the same current that will flow through them. So therefore, we're looking for A says potential across the wire and resistivity. Well, resistivity is correct, same, but potential will not be the same. B, it's talking about resistivity, which is the same, and the current will be the same, so it's got to be B. But let's look at C. Current is same, but resistance will be different because of the cross-sectional area. And D, we're looking at resistance again, which is different, and the potential difference, which is different. So the answer is B. Question 26. So this one is quite tricky. In the circuit below, the initial voltmeter reading is 0. The temperature of the negative temperature coefficient thermistor T is then increased. Which change to the circuit could restore the voltmeter reading to 0? Well, so when the thermistor changes, when the temperature increases, the resistance would have gone down, which means that the voltage will go down because V equals IR. So V is directly proportional to R. So voltage will go down. And if voltage goes down, we would want the resistance of T goes down, we will want the resistance of R2 to go down, therefore it should be A. So decreasing the resistance of R. 27. An electric motor lifts a load of weight W through a vertical height H in time T. The potential difference across the motor is V, and the current through it is I. What is the efficiency of the motor? Well, efficiency is going to be useful power out over power in, and the useful power out will be the weight times velocity, because you're lifting that up, which is over the power in will be voltage times current, and therefore the weight, we know what velocity is. Velocity is d over t, and d is h, so that's h over t. So therefore we need to replace v with h over t, and bringing that there, we're going to get wh over vit, and therefore efficiency equals wh over vit, and this is c. What is the kinetic energy of the object? So we got m as the mass, we got r as the radius, and we got n as the frequency. So n equals f. Kinetic energy is a half mv squared. We know v equals omega r, and v equals to 2 pi f r, because omega is 2 pi f. Now v squared that we got 4 pi squared r squared n squared, because n is f. So kinetic energy is going to be a half m 4 pi squared r squared n squared, and 2 cancel out the 2 from there. You will get the kinetic energy is going to be 2m pi squared r squared n squared, and the answer is C. 29. The graph shows the variation of displacement, time graph, for a particle moving with a simple harmonic motion of period t. So from there to there is a period of t. Now at this point here, the graph is saying which graph shows the variation of kinetic energy Ke of the particle with time. Well, the kinetic energy, the greatest kinetic energy is at equilibrium. So there and there and there are the greatest kinetic energy. There and there and there. So we would, if we were translating that into kinetic energy, that would be the maximum there. So we got the maximum there. You're not going to have a negative kinetic energy, one, because the speed, the gradient is the velocity, and velocity is the squared. So you're not going to have a negative. You're always going to have a positive value. So kinetic energy is scalar, so no negative values. Right, so you're going to get the maximum there, and that will be the minimum there. That will be maximum, minimum, and maximum. So the answer is going to be D. Question 30. Two pendulum A and B oscillate with a simple harmonic motion. The time period of A is 2 seconds, and the time period of B is 1.98 seconds. A and B are released in phase. What is the number of oscillations of A before A and B are next in phase? For one oscillation difference at certain time, they will be in phase. One oscillation difference. So we could try from A, we go 49. We can try 49 times 2, that's 98 seconds. And in ratio of 1.98, it does not work. It's not a multiple of that. When we try 99, we try 99 times 2, we get 198 seconds. And that is, and then we multiply 100 by 198, it will 198 seconds. If we multiply 100 by 1.98, we get 198 seconds. So for B. Therefore, you can see the 2 will be in phase, and C will be the right answer for 99. Is what we need to multiply A by 4 to get the 198, and 100 times 198. So that means they will be in phase. 31. The frequency of oscillation of a vertical spring is F when the mass hanging from the spring is M. What is the relationship between F and M? We know that period is equal to 2 pi root M over K. Period is 1 over F. Therefore, F is 1 over period, which implies that you're going to get 1 over 2 pi root K over M. So F is directly proportional to M to power minus a half, because a root of M is M to power a half, and 1 over root of M is going to be M to power minus a half. So that's where we get, that's 1 over root of M. That's where we got that from. And that's why F is proportional to M to power minus minus a half, and the answer is A. 32D will be the answer in this case because the damping, the amplitude has to go down and slightly squashed, so the amplitude will go down, and the only one that's showing that is D, so the answer is D.